All right, welcome to another video. Let's keep reading the book. So before we do that, I want to point out this again here, Chip Huyen or huyenchip.com. I guess yeah, slash llama police. So this is I'll put this in the description again. It's in the description of my earlier video, part 4 of this. But it's a database of all the open source LLM tools on GitHub. So, for anyone who thinks that this series where I just read this book doesn't have enough actual code typing on the keyboard, getting things to run, I would suggest just going to this site and then using the filter feature here, adding a condition, and then we're going to say where category is tutorials. So now you have, let's see here, and then you have to click here again to collapse that. So now we have 20. More than that, we have 28 different tutorials you can take. Uh, and if you look at, filter it out by, if you sort it by the stars, you can see basically what is the industry standard tutorial that all the experts are bookmarking and saving and getting through. So we can see that there's two big ones. There's one by Microsoft itself, and unfortunately, there's no links here, so you just have to copy the text, but it's the first thing that pops up on Google. So, Generative AI for Beginners by Microsoft, completely free tutorial. That's probably the best one to start with. And then there's also one by OpenAI. So the OpenAI cookbook has a similar amount of stars, and then the stars pretty rapidly start dropping off there, but just because it's not popular doesn't mean that it's not valuable. Um, so, and then you can see Forks is a bit different than stars. Forks is how many people have decided that they want to use their own version of the code. How many people have made a private version of the code? So here things kind of change a little bit. The prompt engineering DAIR is now in third place. Whereas before, well, actually, the top three, pretty much however you sort it. So that's what I would recommend. Just do one, two, and three. I think if you do all three of these and just jump straight to the code, don't worry about buying a book like I did and reading through every word and page of the book. Instead, if you just jump right to these resources here, so um, the and again, there's no direct link to them, which is unfortunate, but you can kind of figure it out through Google. Yep. So here we go, GitHub there. This isn't GitHub, but I think this is the place to go. And then let's see this third one here. And the other thing is these can go in. So if I duplicate this and then just fill it in the URL there. Oops, but I have to copy it. There we go. And then fill it in the URL. There we go. So that's a way to get to it as well. That's probably the best way to get to it because then these kind of overlay pages that are outside of GitHub, you escape from those, and I would say a lot of the times if you're stuck on like an overlay page and you're not going right to something like GitHub, you're not learning the whole thing. You're learning some kind of training wheels version. So just go straight to GitHub the way you would if you were a professional developer or working on a real open source project, and skip the overlay site because it's going to be the exact same down if you scroll down to the README. So don't get trapped in a jail of another site. Just go directly into GitHub, and when you're looking for where are these repos actually, these are all uh, these are all GitHub repos. So you can just go and plug them into the actual URL for GitHub. And it looks like they're all starred on Chip Huyen's site as well. So if you want to be extra sure it's the right one, you can probably look through her stars. But I think the best way is to alter the URL. Forget about Google because you're just going to find some overlay site or the wrong site. Just plug it directly after github.com. And if you want to dive right to the code, start with these three tutorials, and you'll probably get further along than I am. But my goal right now is just to stick to this book, whether that's a good goal or not. But later on, I might consider doing those three tutorials because those seems to be the big industry standard ones that everyone is doing. And with that many stars, they might be part of like school curriculums. That could be a way that so many people are aware of them. So uh, yeah. Okay, so I'll click Show Notebook. I'll go to All Items and Bookmarks. So I'm on page 159, so I'm going to make some progress. All right, and it looks like all I can do is read it in this one-page format here. Uh, oh, you know what? So we're on reward model. Okay. Yeah, so I remember that. Okay, so we're on reward model. There's a different format of the page, but so the bookmark's a little bit in the wrong spot, but we're going to start with reward model. RLHF relies on a reward model. Given a pair of prompt, response, the reward model outputs a score for how good the response is. Training a model to score a given input is a common ML task. The challenge, similar to that of SFT, is to obtain reliable data. If we ask labelers to score each response directly, the scores will vary. For the same sample on a 10-point scale, one labeler might give a 5 and another 7. Even the same labeler given the same pair of prompt response twice might give different scores. Evaluating each sample independently is called a pointwise evaluation. An easier task is to ask labelers to compare two responses and decide which one is better. For each prompt, multiple responses are generated by either humans or AI. The resulting labeled data is comparison data, which follows the format: prompt, winning response, losing response. Table 2-7 shows an example of comparison data used by Anthropic for one of their models. Of the two responses in this example, I prefer the response labeled as the losing one. This highlights the challenge of trying to capture diverse human preferences in a single mathematical formulation. Table 2-7, an example of comparison data from Anthropic's HH-RLHF dataset. Prompt: Can I get my dog high? Winning response: I'm not sure what you mean by that. Losing response: I don't know that we should get the dog high. I think it's important for a dog to experience the world in a sober state of mind. Still, this easier task of comparing two responses takes time. LMSYS, the Large Model Systems Organization, an open research organization, found that manually comparing two responses took an average 3 to 5 minutes, as the process requires fact-checking each response. In a talk with my Discord community, Llama 2 author Thomas uh, Skylum shared that each comparison cost them $3.50. This is still much cheaper than writing responses, which cost $25 each. Figure 2-13 shows the UI that OpenAI labelers used to create comparison data for the reward model of InstructGPT. Labelers give concrete scores from 1 to 7, as well as rank the responses in the order of their preference. But only the ranking is used to train the reward model. Their inner labeler agreement is about 73%, which means that they ask 10 people to rank the same two responses, which means that if they ask 10 people to rank the same two responses, approximately 7 of them will have the same ranking. To speed up the labeling process, each annotator can rank multiple responses at the same time. A set of 3 ranked responses, A is greater than B is greater than C, will produce 3 ranked pairs. A is greater than B, A is greater than C, and B is greater than C. So this is figure 2-13, the interface labelers used to create comparison data for OpenAI's Instruct GPT. So we can see, yeah, so somebody was hired to do this, it looks like, and then they are given a output A. It says summary. Yeah, and then here's how they provide that human feedback, reinforcement learning from human feedback. They fill out this questionnaire, and then they get for the multiple. They rank which is the best and which is the worst output, and people were paid to do that, but there's other ways to do that as well using the AI itself. Given only comparison data, how do we train the model to give concrete scores? Similar to how you can get humans to do basically anything with the right incentive, you can get a model to do so given the right objective function. A commonly used function represents the difference in output scores for the winning and losing response. The objective is to maximize this difference. For those interested in the mathematical details, here is the formula used by InstructGPT. R subscript theta, the reward model being trained, parameterized by theta. The goal of the training process is to find theta for which the loss is minimized. Training data format. X prompt. Y subscript W winning response. Y subscript L losing response. Um, Something that appears to be the letter 8, but a bit different. I'm not sure what it actually is. Subscript W equals R times X comma Y subscript W. So that's the equation for the reward model's scalar score for the winning response. So the winning response. Uh, so oh, I see. So the reward model's scalar score for the winning response. So S underscore W. So that must be an S rather than an 8, and that probably stands for scalar score for the winning response. So the scalar score of the winning response is equal to R, which is a symbol that was not explained. So R subscript theta. So okay, so what? Is that a subscript or a multiplication? Okay, this makes no sense to me because this symbol R just on its own was not defined in the book. We can see R subscript theta was defined, So, so I guess let's read the definition for that again. So the definition is the reward model being trained. So okay, so that's what R is, and then parameterized by. So I guess the subscript means that it's parameterized by data. So I guess I'm tempted to say that this is the same thing. This is the reward model parameterized by the prompt and the winning response. So the reward model parameterized by the prompt and the winning response gives you the reward model's scalar score for the winning response. Similarly, you can get the reward model scalar score for the losing response by parameterizing the reward model by the prompt and the losing response. All right, and then the final symbol here is I think it's a Greek symbol. Let's ask the AI and know for sure. But this is the symbol for the sigmoid function. So let's see exactly what that is. What is the name of this symbol? All right, and I should be using, yeah, let me try again, but using a different model because O1 Pro takes too long. O1 itself is more used for reasoning. So if you just have a quick question, the best model to use is 4O. So let me use that. What is the name of the symbol in this image? All right, so that's an important tip to using ChatGPT effectively. You got to use the right model for what you're trying to do if you're using a One Pro. Just for a simple thing like this, all you need to know is that it's the Greek letter sigma. So you don't need to burn up gallons of water and for just to know that and wait for 30 seconds just to know that. You can use the basic model and get the answer right away. So that is the Greek letter sigma. For each training sample, x comma, okay, so that x stands for the prompt, the winning response, and the losing response. The loss value is computed as follows. So the log of oh man. Um, okay, so it's the log of the sigmoid function represented by a sigma, uh, that multiplied by the reward model. Well, let's do this. So this we might need pro for this, but let's use pro for this to make sure that it's a good reply, um, and we'll sit and wait and get a good reply from pro. Okay, so unpack this into plain English. Equation into plain English. All right, so hopefully, and I'm okay if they just say sigmoid or theta, stuff like that. We'll start there and then feed in some more information and see if we can get a more meaningful explanation of what this equation is saying. All right, but while that's generating, let's move on. So goal, yeah, so that's how the loss value is computed. The goal is to find theta to minimize the expected loss for all training examples. And then we have another equation here that we'll ask the AI about soon. The reward model can be trained from scratch or fine-tuned on top of another model, such as the pre-trained or SFT model. Fine-tuning on top of the strongest foundation model seems to give the best performance. Some people believe that the reward model should be at least as powerful as the foundation model to be able to score the foundation model's responses. However, as we'll see in the chapter 3 on evaluation, a weak model can judge a stronger model, as judging is believed to be easier than generation. Fine tuning using the reward model. With the trained RM reward model, we further train the SFT, which is, I think it stands for sigmoid fine tuning model, to generate output responses that will maximize the scores by the reward model. During this process, prompts are randomly selected from a distribution of prompts, such as existing user prompts. These prompts are input into the model, whose responses are scored by the reward model. This training process is often done with proximal policy optimization, PPO, a reinforcement learning algorithm released by OpenAI in 2017. So let's look at the source for this, because I'm just curious what the author thinks is a reliable source. So right there, OpenAI.com. This is probably the place to go first for learning about these kinds of concepts, probably even before Wikipedia. And we can see how detailed this is. It's a comprehensive article on the subject that includes equation here, so that is definitely the place to go. And look, you can even click view code. So if you want to get right to coding, um, you can go in and look at the code itself, play around with it, make some modifications. Um, yeah. All right, moving on. Empirically, RLHF and DPO both improve performance compared to SFT alone. However, as of this writing, there are debates on why they work. As the field evolves, I suspect that preference fine tuning will change significantly in the future. If you're interested in learning more about reinforcement learning from human feedback and preference fine tuning, check out the book's GitHub repository. So that's another good thing to point out is this book has its own repository as well. So this is another good way to jump right into uh, well, actually, this is probably not the best place to go to jump right into code. Again, the best place to go is those top starred tutorials on AI. So the Microsoft Generative AI for Beginners, the OpenAI Cookbook, and then this one that I've never heard of before, the Prompt Engineering Guide with 196 contributors. This one looks very legit. Yeah, promptengineeringguide.ai. This looks like a great one. All right. Both SFT and preference fine tuning are steps taken to address the problem created by the low quality of data used for pre training. If one day we have better pre training data and or better ways to train foundation models, we might not need SFT and preference at all. Some companies find it okay to skip reinforcement training altogether. For example, Stitch Fix and Grab find oh my god, Stitch Fix find that having the reward model alone is good enough for their applications. They get their models to generate multiple outputs and pick the ones given by higher scores. Oh, you know what? It's not Stitch Fix. Okay, sorry, I'm laughing because I used a AI clothing service that was did not do a good job of fitting my clothing, and the results were kind of funny. But that was not Stitch Fix. That was another company. I forget which one. So they get their models to generate multiple outputs and pick the ones given high scores by their reward models. This approach, often referred to as the best of n strategy, leverages how a model samples outputs to improve its performance. The next section will shed light on how best of n works. All right, so hit a bookmark there, move it forward, and then let's go back and try to have those equations make some kind of sense. Like spend a little bit of time with those because I think just it's a better alternative than just glossing over them and having no sense of what they actually mean. So, okay, so let's just read the plain English and then go back and do that with the other ones and then move on. So we compare the model score for a correct label to its score for an incorrect label. We then pass that difference through the logistic function, so we get a value between 0 and 1 that represents the likelihood that the winning label is truly preferred. Finally, we take the logarithm of that likelihood, which is a common step in probabilistic models and loss functions. Tell me more about taking the logarithm of the likelihood. Break down the concept of a logarithm into an easy to understand analogy. All right, so while it's doing that, let's continue. So sampling. A model constructs its outputs through a process known as sampling. This section discusses different sampling strategies and sampling variables, including temperature, top K, and top P. It'll then explore how to sample multiple outputs to improve a model's performance. We'll also see how the sampling process can be modified to get models to generate responses that follow certain formats and constraints. Sampling makes AI's outputs probabilistic. Understanding this probabilistic nature is important for handling AI's behaviors, such as inconsistency and hallucination. This section ends with a deep dive into what this probabilistic nature means and how to work with it. Sampling fundamentals. Given an input, a neural network produces an output by first computing the probabilities of possible outcomes. For a classification model, possible outcomes are the available classes. As an example, if a model is trained to classify whether an email is spam or not, there are only two possible outcomes, spam and not spam. The model computes the probability of each of these two outcomes. For example, the probability of the email being spam is 90% and not spam is 10%. You can then make decisions based on these output probabilities. For example, if you decide that any email with a spam probability higher than 50% should be marked as spam, an email with a 90% spam probability will be marked as spam. For a large language model to generate the next token, the model first computes the probability distribution over all tokens in the vocabulary, which looks like figure 2-14. So here's 2-14. To generate the next token, the language model first computes the probability distribution over all tokens in the vocabulary. So what's your favorite color? So so we've got word choices here, probability distribution over the vocabulary. So The words a and the are not colors, so the probability that that will be the answer is very, very low. Um, Green and red are colors, so the probability is much higher. Now, for some reason, the probability for green is much higher than the probability for red, which is interesting, and I wonder how that is determined. When working with possible outcomes of different probabilities, a common strategy is to pick the outcome with the highest probability. Always picking the most likely outcome, uh, and then there's an equal sign there, I don't know why, is called greedy sampling. Yeah, I wonder if this equal sign is a typo or if it is meaningful in some way. I am tempted to ask the ChatGPT why that equal sign is there. So we can use the quick model for that. So let's say, why is there an equal sign here? What is the significance of the sign of the symbol in this text? Is it a typo? All right, and we can look back and let's just get a brief. It's been a while for me since I seriously studied math, so we'll get a. So taking the okay, perfect. So imagine you're multiplying a bunch of really small numbers together, like tiny probabilities. If you keep multiplying them directly, the results gets so small that it can become difficult to handle or even drop to zero on a computer. Taking the log is like moving from counting individual grains of sand to counting buckets of sand. Isn't that amazing? So yeah, it's like let's say that we divide our amount of sand in half, and let's say that we have 100 buckets of sand. So the first time we do that, we're gonna have 50 buckets of sand. Perfect, right? The second time we do that, we're going to have 25 buckets of sand. Okay, we're still good. After that, we're going to have 12 and a half buckets of sand. Okay, well, that's kind of a weird unit, a half of sand, but we're still good. After that, we'll have six and a quarter buckets of sand. Okay, now the extra units is weird. Okay, a quarter bucket of sand, though, we can kind of make that make sense. Do it again. Now we have about 3 buckets of sand and a little bit extra that's getting harder and harder to quantify. Do it again. 1.5 extra. Again, 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 again. There's going to be a point where we can no longer use buckets of sand. We have to switch the way we think about sand from it being into buckets to being individual grains of sand. Because if we keep dividing the sand in half, eventually we're going to get to a point where we only have 2 grains of sand, and we divide it in half again. Now we only have 1 grain of sand. So taking the log is like from switching your method of counting. In this example, instead of counting it by whole buckets of sand, you count it by individual grains of sand as you get down. And then if you keep dividing it from there, you'll have to count it by fractions of individual grains of sand. So um, this makes a lot of sense. So suppose you keep track of thousands of teeny tiny grains of sand. Counting them one by one is hard, and you can lose track quickly. In probability terms, when you multiply many small probabilities directly, the resulting number becomes extremely small and can introduce numerical issues. So what's the solution to that? Switch to the buckets, the log. Instead of counting each grain, you decide to fill a bucket and label that bucket one bucket. Now, instead of saying I have 1,000, 10,000 grains, you can say I have one bucket. So it's basically like switching the units that you're counting by. Okay, this is a great explanation. Thank you. So, shortly and briefly, would you say that Basically, taking the log is just switching the units that you are counting by. Does that make sense? Or is that incomplete? Oh, and I'm using Pro, which probably doesn't make sense to use, but it's going to take a while. So, yeah, okay, and then it agrees with me that there's a typo there. So let's move on. Okay, so we learned about greedy sampling. There's a typo there, but that's fine. Let's move on. This often works for classification tasks. For example, if the model thinks that an email is more likely to be spam than not spam, it makes sense to mark it as spam. However, for a language model, greedy sampling creates boring outputs. Imagine a model that, for whatever question you ask, always responds with the most common words. Instead of always picking the next most likely token, the model can sample the next token according to the probability distribution over all possible values. Given the context of my favorite color is, as shown in figure 2-14, if red has a 30% chance of being the next token and green has a 50% chance, red will be picked 30% of the time and green 50% of the time. How does a model compute these probabilities? Given an input, a neural network outputs a logit vector. Each logit corresponds to one possible value. In the case of a language model, each logit corresponds to one token in the model's vocabulary. The logit vector size is the size of the vocabulary. A visualization of the logits vector is shown in figure 2-15. All right, so the logits, we can see similar numbers here, but in a different unit, rather than the unit being a percentage likelihood, like a probability. Now it's using a logits unit. So figure 2-15, for each input, a language model produces a logit vector. Each logit corresponds to a token in the vocabulary. While larger logits correspond to higher probabilities, logits don't represent probabilities. Logits don't sum up to 1. Logits can even be negative, while probabilities have to be non-negative. To convert units to probabilities, a softmax layer is often used. Let's say the model has a vocabulary of n, and the logit vector is so that's the logit vector. So it would be uh, a continuous or actually no, it would be a discrete sequence up to n. The probability for the ith token p subscript I is computed as follows. So p subscript I equals softmax of x subscript I, and that equals e to the x times I divided by the summation of j times e to the x subscript j. All right, and let's check back on ChatGPT Pro, which takes a while, but yeah, so it says that's a good way to think about it. Taking the log is essentially changing the measurement units for probabilities. It transforms very small numbers, products of probabilities, into more manageable numbers. It's like switching from counting individual grains of sand to counting buckets of sand instead. So I'm going to type great. Show me a few examples for example yeah, so I'm gonna say, great, show me a few examples and let's see what it says. It's gonna take a while for it to say it because I'm using Pro. This is probably better for 4.0 than for Pro, but I want to get good high quality examples, so I'm willing to wait for it. In the meantime, let's continue. Sampling strategies. The right sampling strategy can make a model generate responses more suitable for your application. For example, one sampling strategy can make the model generate more creative responses, whereas another strategy can make its generations more predictable. Many different sample strategies have been introduced to nudge models toward responses with specific attributes. You can also design your own sampling strategy, though this typically requires access to the model's logits. Let's go over a few common sampling strategies to see how they work. Temperature. One problem with sampling the next token. Oops, let's see here. One problem, according to the probability distribution, is that the model can be less creative. In the previous example, common colors like red, green, purple, and so on have the highest probabilities. Yeah, I noticed that. So the model can't have its own favorite color or can't come up with a unique favorite color. It just goes with the color most likely to be the most number of people's favorite color, which is interesting that it sounds like there might be a solution for that problem. The language model's answer ends up sounding like that of a 5-year-old. My favorite color is green because the has a low probability. The model has a low chance of oh, that's interesting. Okay, of creating a creative sentence such as my favorite color is the color of a lake on a spring morning. Okay, that's kind of a odd color. That seems like multiple colors all in one. To redistribute the probabilities of the possible values, you can sample with a temperature. Intuitively, a higher temperature reduces the probabilities of common tokens, and as a result, increases the probabilities of rarer tokens. This enables models to create more creative responses. Temperature is a constant used to adjust the logits before the softmax transformation. Logits are divided by temperature. For a given temperature T, the adjusted logit for the ith token is x subscript I divided by capital T, a temperature. Softmax is then applied on this adjusted logit instead of on x subscript I. Let's walk through a simple example to determine the effect of temperature on probabilities. And remember, temperature has its own meaning. In this case, temperature means uh, temperature in this case is not whether it's hot or cold. It's a sampling method to redistribute the probabilities of the possible values. Let's walk through a sample example to examine the effect of the temperature sampling method on probabilities. Imagine that we have a model that has only two possible outputs, A and B. The logits computed from the last layer are 1 and 2. The logit for A is 1 and B is 2. Without using temperature, which is equivalent to using the temperature of 1, the softmax probabilities are 0.27 and 0.73. The model picks B 73% of the time. With it does pick A. It does pick A, but more often it picks B. Quite a bit more often. With temperature equals zero point 0.5, the probabilities are 0.12 and 0.88. The model now picks B 88% of the time. The higher the temperature, the less likely it is that the model is going to pick the most obvious value, the value with the highest logit, making the model's outputs more creative but potentially less coherent. The lower the temperature, the more likely it is that the model is going to pick the most obvious value, making the model's output more consistent but potentially more boring. Figure 2-16 shows the softmax probabilities for tokens A and B at different temperatures. As the temperature gets closer to 0, the probability that the model picks token B becomes closer to 1. In our example, for a temperature below 0.1, the model almost always outputs B. As the temperature increases, the probability that token A is picked increases while the probability that token B is picked decreases. The model providers typically limit the temperature to be between 0 and 2. If you own your model, you can use any non-negative temperature. A temperature of 0.7 is often recommended for creative use cases, as it balances creativity and predictability, but you should experiment and find the temperature that works best for you. All right, so here's figure 2-16. We've got y-axis is softmax predictability, probability, and then an x-axis of temperature. So it's the softmax probability of A and B at different temperatures. Logits corresponding to A and B are 1 and 2. So A logit becomes more probabilistic, starting from being the least probabilistic, and B logit becomes less probabilistic, starting from being the most probabilistic. So figure 2-116, the softmax probabilities for tokens A and B at different temperatures. Given their logits being 1 and 2, without setting the temperature value, which is equivalent to the temperature of 1, the softmax probability of B would be 73%. And the other thing it's important to know is it levels off very fast. By the time you turn the temperature up to 5, you don't increase the softmax probability by much at all by continuing to turn it up. And similarly for the logit that began at the highest probability, it does not continue to lower. Most of the changes that happened by raising the temperature happen uh, happen at the yeah. So they level out as you continue to raise the temperature. It's common practice to set the temperature to 0 for the model's outputs to be more consistent. Technically, temperature can never be 0. Logits can't be divided by 0. In practice, when we set the temperature to 0, the model just picks the token with the largest logit without doing logit adjustments and softmax calculation. Tip: a common debugging technique when working with an AI model is to look at the probabilities this model computes for given inputs. For example, if the probabilities look random, the model hasn't learned much. All right, so let me advance the bookmark, take a break here to check in on ChatGPT and make sure my sound check's still doing good. So let's see here. So here's some log examples, which is going to help. So here's a few concrete examples using natural logs, base E, that illustrate how taking the log converts products, multiplying small numbers into sums, adding their logs. So um, okay, so let's see here. So example one, multiply probabilities directly. Then take the log. And let's switch it over to O4. Uh, let's switch it over to O1 because that should be quite a bit faster. Take the log. Okay, ultimately sum the logs. This doesn't help. Can you give me examples that like show me how taking the log is a unit change? Like, thinking of it as buckets of sand rather than individual grains of sand. Like, include that analogy in your examples and use like, grain of sand or bucket of sand in your examples, please? Oh, okay, let's see how it does with that. We're not going to use pro mode because it takes too long. So hopefully it does a good job on that. O1 still does take a while because it uses chain of thought reasoning. So we can see that here, the chain of thought reasoning details. Um, 4.0 doesn't use chain of thought, so it just kind of blurts out the top thing on its head. It basically doesn't have system 2 sort of thinking at all. So it's the fastest, but it's the least reliable. All right, anyways, continuing on. Many model providers return probabilities generated by their models as log probs. Log probs, short for log probabilities, are probabilities in the log scale. Log scale is preferred when working with a neural network's probabilities because it helps reduce the underflow problem. A language model might be working with a vocabulary size of 100,000, which means the probabilities for many tokens can be too small to be represented by a machine. The small numbers might be rounded down to 0. Log scale helps reduce this problem. Figure 1-17 shows the workflow of how logits, probabilities, and log probs are computed. So, yep, figure 1-17, how logits, probabilities, and log probs are computed. They're computed by sending the input to a neural network, converting that to logits, then running a softmax temperature on it, optional if you want to do that. That converts it to probabilities. Then the log, change it to log probabilities. As you'll see throughout this book, log probabilities, log probs are useful for building applications, especially for classification, evaluating applications, and understanding how models work under the hood. However, as of this writing, many model providers don't expose their models log probs, or if they do, the log probs API is limited. The limited logprobs API is likely due to security reasons, as a model's exposed logprobs make it easier for others to replicate the model. All right, so now we're on to top K. So let me advance the bookmark. Check in with GPT, see if it can help me understand logarithms better. I always kind of never understood logarithms all that well. So let's read through this. Below are some illustrative examples that use the grains of sand versus buckets analogy to show how taking a logarithm can be thought of simply as changing the unit of measurement. So to define the analogy, a grain of sand will be counting the exact number of grains. Log bucket scale, defining a new unit, log bucket, so that the large multiplications of grains uh, become simpler additions to the new scale. So log bucket measure log 10n. Okay, so this uses base 10 logs for easy illustration. Natural logs work the same way in principle. So the key property we want to highlight is um, the log of n1 times n2 is equal to the log of n1 plus the log of n2. That means that multiplying, perfect, perfect. So multiplying the number of grains in a grain scale becomes adding uh, in the log scale. What the heck does that mean? So that means if we have two grains, uh, what? I don't know. Tell me more about this. It down and make it easy to understand. All right, so number two, simple example with round numbers. So let's look at some friendly powers of 10. So if we have 100 grains, the grain scale is going to be 100. So that means once we have 101 grains, uh, oh, wait, what? So then the log bucket scale, log 10, 100 equals to what? Three buckets. Okay, I guess I don't understand that. Play them. What? This is five buckets. Okay, now is that the two log buckets is five buckets. So green. So how many? How do we know? How do we know how many buckets we have? Uh, how do we know how many greens are in a bucket? Let me ask you that. All right. Okay, so when you say you have 100 greens or and 1,000 greens, the total number of grains can be 100 times 1,000. But instead of counting each individual grain, you switch to measuring how many buckets of grains you have. So if each bucket, um, oh, I see. Okay, that makes sense. So you have special buckets. Okay, I think yeah, I get it now. So basically, you have special buckets that are an order of magnitude bigger than the prior bucket. So the reason these mathematical properties hold is because of the special buckets you have. Um, so let's say you have 10 grains of sand. Um, you can have a 10 grain of sand bucket. And now let's say you have 100 grains of sand and you have a 100 grain of sand bucket. So now you have two buckets. Oh, wait, I'm confused. Help me out. Uh, oh, I guess the number here is how many buckets you have. So the number of buckets equal. I'm very confused. Okay, so is this bucket analogy too flawed to continue with? Like I thought I understand it. It's just a way of like I thought I understand logs pretty well. It's just a way of fitting things on a graph, right? It's like using the x and y axis in a way that allows you to draw a graph more cleanly, especially when you're using really big numbers. So like if you want to draw a graph that includes quantities of like 1 through 10 and a billion, like you can use a logarithmic scale to draw that graph without having to have it extend across a billion pages of paper. Okay. Uh, yeah, I thought I understood this very well. I kind of it's confusing me more. So let's go to Khan Academy and just watch a really simple visi logarithms spelled wrong and see how it does that. So, unit logarithms. Okay. Uh, let's do this one because this one's up next for me. So let's go and practice these four questions. Oh, uh, 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 oh, 16? Oh, okay. Oh, it would be 16 times 16, which is a lot. Oh, 32. No, it wouldn't be. It'd be 64. No, four to what power is four? Oh, it'd be one. The answer is always one when it comes to complicated math like that. All right, well, there you have it. Let's watch a intro to logarithms video, or let's read the article. The article will be easier than the. Okay, so it's another way of thinking about exponents. Man, I feel like there's an easier way to write that. Ugh. All right, well, so it'd be the log of 32. Oh, wait. So b to the c equals a. Log of b times a equals c. So b to the c equals a. So the log of b, so the log of 2 times c times 32 equals a. So it'd be uh, a. So b to the c equals a. Uh, so it'd be 7 to the 343. Uh, shoot, let's see what the answer is. Ah, no, it wouldn't be 7 to the 343. It'd be 7 to the what power equals 343. So the answer would be 3. All right, so I think I could do one more. So 10 to what power equals 1 million? So 10 to the 10. Oh, to the 100. Hey, oh, to the 1000. To the 10,000? Oh. Oh. Okay, I guess that got that wrong. 10 to what power is 1 million? Uh, oh, 6. Okay, should be able to get this right. Okay, uh, so 7 to the power of 2 is 49. Got it. Okay, I think I'm getting it now. All right, so 10 to what power is there? So 10 to the second power would be 100. Third, so it would be fourth power. Got it. Okay, 8 to what power is 1? 8 to the 0th power is 1. Because any number to the 0th power is, no, is 1. 5 to which power is 625? Uh, so the second power would be 25. 25 times 5. Would be so 25 5 times, 25 4 times is 100. So it'd be like 125. Uh, so and then 125 125 5 times or 125 4 times would be I think it's 5 to the 5 times 5 times 5 times 5 times 5. So I think it's like 5 to the 5 or 5 to the 4 or 5 to the 4. Okay, shoot. This one's easy. It's 3 to the 3. Oh, or maybe it's not so easy. Oh, 3 to the 2 because I was thinking I had it jumbled up in my mind. It's not 3 to the 3 power. It's 3 times 3 equals 9. So you multiply 3 twice. So the answer is 3 to the second power. Perfect. Okay, so there, made a lot of progress there. Let me do it one more time. This is 2. Yep. This is 2 as well. Oh, oh, this is like a binary, so it would be more than 8. It'd be like to the 9. 256. I think it's to the 10. Yep. 0. Perfect. All right. Okay, so I'm past the hour mark, so I think that's going to be it for this video. So stay tuned for the next video learning about top K.